Thank you very much, Visu, and thank you overall for the very nice words, the introduction, and the invitation to this workshop. I have to start by saying that I'm very unhappy I wasn't able to make it, although I have a very happy personal reason because we got a new family member. So I would have wished to spend these 2 weeks with you, which probably has been quite, as understood, very complete and really covering the whole subject. So I'm not sure if I'm going to contribute anything really new to what you have already been listening for this almost 2 weeks, and you will keep on listening. But so please, first of all, forgive me if I'm going to repeat some things that you already know. I'll try not to. And I'll try not because I want to assume that now you have a quite thorough understanding of the theory and of the concepts around tipping points and resilience and early warnings and indicators and dynamical systems and bifurcations. So, and I would like to ask a question that I find at the moment more interesting and more important, given all the big ecological, I'm an ecologist, so all the big ecological problems that we are facing at the moment. So how can we use these tools, these very complete theoretical tools to make better conservation management or understand something better about how ecosystems work around us? And I think that's what I try to capture on my title, which I don't think it's the best because I'm not really going to talk about decision making per se, but try to think that I'm asking the question of how can we use this in a more practical way to make actual sense of the world around us and help us to better navigate our human actions. So with this, okay. So basically, like a short summary, we're looking at these 3 things. This is what I have in my experience and from the way I view the literature. They're like the 3 ways that we're measuring resilience or changes in resilience. And with this, let me make a little parenthesis, one more parenthesis, and say that with here resilience, I'm talking about this general capacity of the systems to recover after a perturbation, basically the persistence or the capacity of a system to maintain its own state. So I'm not really going to talk 100% about tipping points, but it could be about resilience preceding tipping points, but I'm talking more about, like resilience in terms of the stability of a system to lose its present state and move to something else that could be an alternative or not. And the 3 ways of measuring this, as you have been listening, I guess, all these days, are just measuring changes in recovery rate. So talking about this here, over time or over a gradient of a stressor, or measuring increases in variance and autocorrelation. And basically, I have circled these 2 because these are the ones that are really the ones that we have been mostly focusing on, because doing this thing on recovery rate requires some sort of existing disturbance, or like that usually it's very hard to perform experimentally on a bigger scale. So most of the work we have been doing is focusing on these 2 statistical changes, and there are plenty of ways of doing that. This is not a comprehensive list, so again, another apology for if things are missed, but we have a lot of things, but again, I highlighted, basically we're looking at 2 or 3 statistics. The way to analyze them can be very, very, very different. It can be more sophisticated, more simple statistical moments, but basically we're looking at this at these things. And there are, as I said, plenty of tools. In my categorization, because I'm coming more from, let's say, from the method developing side, I could group this world or this family of signals into 3 boxes. What we call the demographic or ecosystem state indicators, which are basically analyzing time series and spatial data. That's mostly, I think, what you have been talking about during the workshop. Then there are like other types of indicators that could talk about the structure of a system. So we can call them like a structural warning signals. And lately they have been also, like developed another family of signals that is more like the trait-based, looking at traits of organisms and try to understand their resilience. But I'm focusing mostly here because this is where we actually have a clear and mathematically based and model independent expectation of what they mean, what these signals mean. So what this increase in variance and correlation means. So I'm talking about this family of indicators. And let's go to our question. So how do we manage to operationalize, if we manage at all? So I'm going to say basically the obvious, but I will try to back it up with some examples of how we're trying to do that. So just to summarize already, and then you can forget about the rest of my talk. Well, very, very straightforwardly, we can operationalize it by just being able in real time to track changes, to monitor changes in resilience, either within an ecosystem or a given site in place, or for a given species or a population of a given species. And this is basically measuring resilience in time, I would say. Well, the second is if we have more places, ecosystems, or populations that we're interested in, then we can do this large-scale mapping of resilience and then try to rank differences in resilience across space. So this would be like more of a resilience in space approach. And then by doing this ranking, we can identify potential hotspots or cold spots, meaning like places or populations that are apparently more low in resilience. And that's where we should focus our conservation efforts, contrary to cold spots, where maybe we don't really care so much about them, or not really care, but I mean that we don't need to prioritize and spend effort and resources on them. And then the third, which I think is a little bit more underdeveloped, because the first two, I think, is what we have been mostly doing in small scale examples. But the third is like try to understand this type of changes in resilience, either across space or across time. And what I mean understand is like try to connect them to potential drivers. Actually try to understand if there are specific external conditions that favor or disfavor these changes in resilience. And by doing this, perhaps we can highlight what we should be focusing our efforts to manage and change in order to protect a given system. And again, like as you have been listening from the perspective I'm starting my presentation, I'm again thinking of changes that are all negative, like we are all assuming a loss of stability that will lead to something that we are not in favor of. And of course, we can turn the coin upside down. And of course, we can do the same if we be willing to study systems that are in a state where that is not favorable and we want to reverse it. That's also, we can do the same exercise, basically try to understand, for instance, if that reverse path, especially for point three of the drivers, if the path to recovery, it will be mostly affected by the same drivers as the path to collapse. So keep an open mind on that, because most of the literature is, of course, trying to avoid the bad, but also we could focus on the positive. And I think there are more speakers that are going to focus on that. So let me just give you a set of examples of work that I have been involved, or others, about how this could potentially work or has a potential to work. So let's start with monitoring changes in a given system, like resilience, basically measuring resilience in time in order to devise a type of early warning. So this is the example of forest decline in California. And on the top panel, you have the NDVI, the Normalized Vegetation Index. This is a typical proxy that is used for I hope you have, I get a message that you can see my screen. I hope you have always been able to see my screen. Okay, so I'll continue. So the NDVI is it's a typical proxy of vegetation that is recorded through remote sensing satellite data. And this is basically, you know, like the time series of this index that represents basically the density of the forest, of a forest patch in California. And you see that from the record, it doesn't look that much is changing, apart from the fact that we know that we have these strong mortality events happening at around 2014 to 2016. And here what the authors have shown is that by estimating autocorrelation, using not a moving window, but a different approach, using autocorrelation on these NDVI signals, they were able to see that the signal was crossing a potential threshold of indicating a sharp change in autocorrelation quite a few years before they got these big mortality events. So, you know, it seems that, you know, like in this example, that they would be able, by just doing this type of analysis, to see that there was some kind of statistically extreme value early enough in order to perhaps mitigate the potential abrupt mortality event that this forest patch has experienced. So this is one specific example in a given space and time, of course, a posteriori, that things could work. Another example very recently published and that has attracted a lot of attention also is the slowing down of the thermal line circulation. This is the Atlantic circulation that brings warm water from the Gulf of Mexico to the north coast of Europe. And this is a circulation pattern that has been on and off in the past thousands of years. So there is a lot of mechanistic understanding that it is possible for this circulation to abruptly collapse. And it's one of the elements in the climate that has attracted a lot of concern because of that potential eventuality and of signs that is already slowing down. And if that's the case, then the climate, at least for Northern Europe, will be hugely affected. And here what the authors have showed is that by using, sorry for the bad slide, but they're using different indices like sea surface temperature at different latitudes. They measure changes in variance or the evolution in time of variance and autocorrelation, and they reported in all cases, you know, like a consistent, at least statistically, increase in that slowing down. That actually, you know, adds more support to the argument that indeed that circulation is slowing down, and that eventually slowing down means its potential stopping. But as I said, these are like more case-specific approaches in space or in time. The one of the climate is an ongoing. It's actually trying to measure these changes at the same time compared to the forest, where usually, you know, as we have been doing, it's a posteriori manifestation of that potential appearance of that early warning. And of course, that has to do with the availability of the data to some extent. But that thing can be, that availability of the data can be a little bit, you know, like overcome when we try to look at changes or differences in resilience across space. So talking about the second point here, where we can map and rank changes in resilience across different sites. Here, I want to present you some work that we have done on trying to understand whether we can project places of future of future increase in climate variability that could be associated with higher climate sensitivity or instability. So here we're not using anymore the present record, but instead we're using the outcome of the climate projection models that are used to make climate predictions and feed the IPCC reports. So what we did was to compare the projected temperatures, so at the end of the 21st century, compared to the variability that was observed in the historical record at the beginning of reconstructing temperature profiles. So we have what was the variability in the past, early in our observations, and we want to compare if that variability will change in the future based on this, on the output of the climate models. And we didn't only use one climate model, but we used output from 37 models. So actually, we based our conclusions on comparing what 37 models had to predicted of how the temperature would look like in the future. So by doing this, we were able to construct a map of changes in future variability that would indicate climate instability. And with the red, you see these are the places where we will have an increase in variability compared to what has been observed in the past. Whereas with the blue, these are the places where there would be a decrease in variability. So first thing to observe is, of course, that you have this heterogeneity in the result. There are places where you will have an increase in climate variability compared to places that will have a decrease, which is something that is expected because there are a lot of heterogeneities in the climate across the Earth. But still, this is something to keep in mind, that where we're talking about big systems, even if they have the same rules, they can behave very differently based on some more local conditions. The second thing that we observed is this hatched, these lines that you see on the map. These are the places where we got most of the agreement from the output of the 37 models, which actually was also something interesting, given that we always assume that the models will behave in a similar way. Nonetheless, we see that the agreement is not always guaranteed. In any case, here with the circles, I have highlighted areas like the Amazon, the south of Africa, the Sahelian region, and here places in Southeast Asia and Australia, that seem to be the most vulnerable and will have an increase in variability up to almost 15% compared to the historical record. With this type of information, we were also able to construct a map and actually, like highlight something that has been demonstrated or also in the past about this climate injustice, meaning that if you plot countries per GDP, so how rich a country is on the x-axis, and you plot here on the y-axis what we found, like how much variable the climate will be in the future. Here, like there's more variability above zero and less variability below zero. You see that the rich countries tend to fall into the less variability, which perhaps means less climate sensitivity and less instability, whereas the poor countries are the ones who are going to be suffering the most. Here, just for your information, I plotted a point to where India is located, especially on the countries that are going to experience, at least based on these outcomes of the study, more future climate variability. Now, we can also do that or do something similar, but on already existing data. I'm going back to remote sensing data, and I'm going back to vegetation proxies. This is not NDVI, but this is another proxy for measuring vegetation cover through remote sensing. And here what the authors did was like to look at global vegetation patterns of resilience. So they used the record from the last almost 30 years, and they indicated places where they found either that not variance or autocorrelation has increased, or both variance and autocorrelation has increased. And here you see the different colors uploaded in the map. You see also a lot of heterogeneity. You see that, you know, based on what we know from the theory, both indicators should show a positive effect. And that would be the case for 10%. But you see that there was like quite a large proportion that you could get one indicator showing something is happening, whether the other one would not showing that something is happening. So these are at least for my side, you know, like very nice attempts to try to create something that could give and visualize that information of whether resilience is changing, how it is changing on such a global scale. But however, it's to some extent not really usable, apart from giving us a snapshot of what things are happening. So that's why I think going and trying to understand changes in resilience could help us, because getting big pictures like big overviews as the previous ones, as I just explained, it's very hard to interpret. The first thing to do, of course, is to be able to go on the ground and see and verify that the changes that we find are the ones that are reflected from these remote sensing exercises or not. But this is, again, logically quite difficult, and definitely something to pursue, but I don't know exactly how and what scale. On the other hand, if we can combine this information with other available information, maybe we can get a bit of more of understanding of these changes in resilience in order to understand whether they make sense or not, and how to cope with them in order to take a decision. So I'll go and talk about a project that we did on trying to look at about lakes, how we can do that with lakes. So here we used again, remote sensing data, but now we look at lakes that we know lake dynamics a bit more more in depth, and we looked at their trophic status index. Basically, that's a proxy of productivity in the lake, how eutrophic a lake is. And in this 10 years record, it's quite short, I would say, but still we try to identify, on the one hand, what is the overall variability, what's the variance during that period measured in that lake, but also the change in variability. And again, we know we came up with mapping these results, and again, you see quite some variation. You see that there are some lakes that are overall more variable than others based on the coefficient of variation. And here, in terms of the trend, which is something that we are more looking in terms of resilience, you see that, you know, half of the lakes in the distribution seem to show something is happening, whereas in the other half, nothing seems to happening, or actually is the other way around. What else we tried to do was, like, we tried to see if, since we have the pattern of the dynamics of these lakes, we tried to see, you know, like whether these lakes had actually experienced some type of shift. So here on the blue line is actually the record that we have been measuring. So from the remote sensing data. And on the reddish line here, this represents the variance that we have measured in the record. So this is our proxy for variance, on which we estimated the change in variability over time. And the vertical lines represent a regime shift analysis. So we try to look for abrupt shifts. And so abrupt shifts basically meaning that you have a statistical change from one part of the record to the next. So here you see, for example, that for this particular lake, we had one and a second abrupt shift. And here in this one, we classified that as a potential tipping point, because that abrupt shift was associated with an increase in variability, shortly before the shift. Again, this is to be interpreted with a grain of salt, but we try to be very very strict on how we would classify this type of shifts as potential tipping points. So here we're trying to make the connection between what we find as changes in resilience in terms of change in variability to actual abrupt shifts in the time series. And when we do that, we see that we report only a handful of lakes out of our 1,000 record that we did find this type of abrupt shifts. And actually we see that half and half of them were shifted from a low to a high productivity regime, but also we had the opposite result. This would be like the positive change out of something that was more productive, more eutrophic became oligotrophic. These were like more our candidate tipping points. And so we were hoping that now, okay, we have identified where we'd have this tipping point examples, but also at the same time we had this proxy of resilience based on their change in variability. So the idea would be that we could, rank these points based on this criteria. If it was not very clear, I will repeat. So what we did here, we said, okay, here we have for instance, on the x-axis, we have the average productivity in the lake, and here we have the change in variability that we measured. So based on our expectations, we would expect that here in this corner, lakes that are more productive and had showed a high variability, that would be like the ones that had the less resilience and more prone to change to a high productive regime and suffer a tipping point. Whereas here on this quadrant, we would have exactly the opposite. Here would be the good examples. And what you see is like, okay, the lakes are distributed all over, and the ones that where we did identify a potential tipping point were all around the place. So actually, for me, this is a little bit disappointing because, yeah, we were not able to find most of the tipping points, like lakes focused here. On the other hand, it shows that, yeah, we need to, as I was saying before, we need to approach this more large-scale studies with caution and try to find out, on addition, other potential drivers that are affecting this dynamics. So we tried partially to do that in this example by building a model where we try to see what would affect the probability of a regime shift based on some characteristics of the lake. We had a lot of climatic, environmental, and lake properties. At the end, the model, gave us very few potential explanatory variables. Basically, the lake depth was an important variable, the latitude where the lake is situated, and strangely enough, or interestingly enough, the GTP at the level of the catchment around the lake. And what we found was that we could partly explain that probability through these variables that are indeed affecting variability in the lake, but mostly affecting the overall variability rather than the trend in the variance, so like the change in stability that trend in variance would measure. So in this case, we were not really able to improve our understanding in terms of identifying potential regime shifts. But again, as I said, this was like a 10-year record with a lot of gaps, I have to admit. But nonetheless, it gives like a roadmap ahead. I think if we perform this analysis in the future in a longer data and perhaps, like focusing on more different subsets of lakes, we can improve that capacity of detecting probabilities of regime shifts. And I want to finish with, I think I have another 5 minutes maybe, with another example from forest. So here again, it's not vegetation globally, but this is a study we recently published on just focusing on forest dynamics, where again, we looked at NDVI, same suspect. We will be seeing a lot of studies using this proxy in the future on the similar topic. And we just measure the trend in autocorrelation, so the change in autocorrelation. And here is the map that we got. This is only forest. In the previous study that I described to you was overall vegetation. It was any type of ecosystem where you could find vegetation. See, here we focus on forest because by doing this, you know better how forest behaves. So this is just a mapping where you can see again this huge heterogeneity, places where in the last 20 years there was more or less slowing down, that change in autocorrelation. But here we could also start understanding more the system by looking at how, if we would project these changes on a ecological axis, or sorry, niche space, how things would look like. So, for instance, here on the x-axis, we have annual precipitation, so rainfall. So here's more dry and here's more wet places, and here we have the annual temperature. This is more warm forest versus cold forest. And what you see is that as we kind of already know, it makes kind of sense that we see that the precipitation doesn't have such a big effect compared to temperature. You see more for places with higher temperature is the places where autocorrelation, that slowing down, seems to be affected the most. Also, when we try to look at some drivers that are affected across, are affecting changes in autocorrelation across the latitude, and we had 3 potential drivers. One was for how much forest is actually there. That is also a proxy of forest degradation. The other one was the background climate, and the third one was the climate variability. And already you see that like forest density doesn't seem to have such a big an effect, although it could be argued against based on what we know. But you see that the background climate was quite a strong driver for positive changes in autocorrelation, and climate variability, like the variability I pinpointed to you with that modeling slide. You see that it seems to have a very strong effect on forest autocorrelation at around the tropics, like basically the Amazon basin. So this already starts to give us some understanding of which drivers to focus more or not in trying to understand changes in resilience. Nonetheless, it proves not that these changes in resilience are actually meaningful, again, as I had pinpointed at the beginning of the talk. And here we tried to do a little bit, to do a bit something bold, I would say. So we try to estimate the risk of resilience loss. Basically, we had this map, and so we had this map of autocorrelation of forest across the globe, but for some parts of this forest, we have been able to identify also in the record some abrupt declines, some regime shifts like the ones we have identified for the lake productivity dynamics I showed you earlier. So we knew, or we could find out where in forest patches we have an abrupt decline. And the year before that abrupt decline, we had estimated a value of autocorrelation, a value of resilience. For the same patches, we also had all these other the types of information, as I showed you, like the forest cover, the climate variability, the background climate, and some other environmental and climatic variables. So we were able to build a model that would predict, based on these variables, the estimated temporal autocorrelation on this, where we actually found an abrupt decline. Now we have this, we build this model, and using this model, we try to predict the autocorrelation or the distance of autocorrelation of the places where we have not yet seen an abrupt decline in the rest of the globe. It's a bit complicated, I will repeat. So we have this model where we in theory, we can predict the temporal autocorrelation that we will get an abrupt decline given a set of environmental variables. So now we use the environmental variables for the places that we have not yet experienced an abrupt decline, and we predicted what the temporal autocorrelation should be. So we have a predicted autocorrelation for places with potentially could have an abrupt decline, but also we know their observed values. So we may just estimate the difference. So if the difference was negative, that means that these places have passed the expected autocorrelation where we would find an abrupt decline. And in cases where this difference was positive, that means we're not yet there. And again, now we plot all these places on this ecological niche of temperature and rainfall. And you see that we have the majority of the points, the gray points, are the places where still we are not there yet. However, you see in some of them, there are this light gray area. It means that we're very close to that value that potentially could mean that an abrupt decline is around. And we have some places where they have already passed. We have already values of autocorrelation that are indicating to be past their abrupt decline, although we have not been able to see it in the record. So again, as I said, this is like a bold exercise, but this shows a way that by harvesting this information and combining it with other environmental and climatic variables that we call drivers, we can build models and start making potential estimates of risk, actually indicating risk maps of resilience decline that could be associated with abruptness, with abrupt decline, not just decline overall. All this idea, I think, it basically is on for or aims at something more ambitious, like being able to build a type of sensing systems for resilience at the globe scale, which of course with a lot of challenges ahead, but also a lot of potential that I hopefully have been able to explain to you and demonstrate to you with these examples today. Thank you very much for your attention.
It's time for questions now. Questions? So we saw a lot of data now. We have moved from hardcore theoretical concepts to how to apply to data. So Smita, you have a question? Yes.
Hello. Hi, sir. It was nice talk. I want to know a little more about the second point that you mentioned, map or rank resilience across site, space, or species. So I have read articles where they rank species, like if I have a multivariate multi-species system, so I can rank the lowest or highest degree of resilience. Can you elaborate a little on how we can do it across space? Is there some way we do it across space, ranking resilience?
Thank you. You say across space?
Yes, sir.
Yes. So maybe it wasn't very clear, or didn't explain it enough, but like in this example that I saw with forest, the resolution of that map is a forest patch. So that would be like 1 kilometer by 1 kilometer patch. So if I want, for example, to rank this in this forest exercise, different patches, I know a value of resilience for every patch. So I can rank them basically on that value of resilience. So I can, in that sense, in other ways, I will discretize space in whatever scale I want, 1 by 1 kilometer or 1 hectare by 1 hectare, and I can do this ranking. Or I can, like think of bigger scales, for example, and I want to rank the Amazon forest versus forest in Australia. So we decide the scale in space, and then we can do the ranking afterwards. Is that more clear?
Yes, sir. Just one more query. Does deciding the scale at which we would calculate the resilience of these patches affect my outcome?
I think so. That's a very good question, and it's a very difficult question because then that scale will depend on the system that you are studying. That's why in these big estimations, for instance, of vegetation dynamics across the whole globe, where you have dry land versus grassland versus a forest, the scale, maybe it's the same measured in these studies, but the scale can have, as you said, very big consequences. So at least if I only do forest, maybe I can be more safe with the scale I choose, given that, I don't know, like a forest, needs to or performs its processes on a scale, let's say, of a kilometer, whereas maybe a dry land, maybe a kilometer is a very, very, very long, very, very big scale. You see, so it's absolutely a great question and a very difficult question. It has to be answered, has to be system specific.
So, sir, is there theoretically, I think can it be determined theoretically that how do I choose the scale, or it needs empirical investigation?
I think you can answer it theoretically, but again, first you need to define the system. So you need to talk about a specific type of ecosystem, as we said, for instance, forest, a specific type of tree, given, I mean, the lifespan, for example, the life history of that organism, and then through this you can derive what should be the appropriate scale. Having said that, because we are also, I know maybe theoretically we think we could do a lot of things, but I won't find a bad exercise as following your lead, like to perform this type of work that we're using with remote sensing and changing the scale and see how much this affects our results. Because maybe we find out that even if we assume that scale is important, it can be that scale is not as important as long as we are within some reasonable boundary. So it's a nice question, not only theoretically but also empirically, to test on the data, on this remote sensing data.
Thank you, sir.
You're welcome.
Thank you, Smita. Sudipta, yes.
Yeah. So in your analysis, actually, you have used the current data, but you are predicting something future kind of thing. But in actual system, some of the environmental noise, or maybe the system has changed completely over time. So then how this prediction will be useful for making some kind of decision?
Yeah, it's the handicap of doing this type of large scale analysis, that you don't know, you assume that all these sites that are recognized remotely as forest or grassland or dryland, we assume that they are in a given state. So what we would need to do is we would need to combine this with some surveys, some on the ground surveys to confirm these expectations. On the other hand, this because you are using bigger data sets and bigger scales, you kind of assume that the law of big numbers will compensate for small anomalies within your data set. But it's an open question, and I think it's not only a question for this particular exercise. It's a general question about using remote sensing data, right, and remote sensing products.
Any
But
other
here,
questions?
if I may just here, I think with these studies, I think this is more like the eventuality, the potential that is there. Of course, there's a lot of work because now this work, if I make a parenthesis, is not possible because we have 20 years of data. If you ask me 5 years later, I would say I won't do that because 15 years is nothing. 20 years is still nothing, but at least you can do the statistics with some caution. You see what I mean? So in theory, the data will be only better from now on. So we can refine some of these insufficiencies, I think.
Vasilis, I have a question. So we have 20 years time series data, let's say of NDVI and so on, right? I mean, our theoretical work also shows that if we can exploit the spatial data, we can add sort of, good power to it. Have you tried doing that so far? Because we have analyzed global data sets of NDVI. Have you looked at spatial metrics?
Not yet, not yet. This is, as I said, this is work in progress. This was already, for me, the time is the first, let's say, the first step to do. If you think then you go on space. Then you add the second dimension already.
Yeah, I mean, also the calculations and statistics becomes harder with space, much more than just time alone. Yeah.
Yeah.
Any other questions? Okay. And these are all NDVI data sets at 250 meter resolution. Is that right?
Excuse me?
The NDVI data that you showed, those are at 250 meters resolution. Is that right?
I think so, but I want, because I'm not so much good with the details, because also there have been some change in the satellite they are using. So I can't say, I can't confirm that if this for the whole record is that resolution or that there's changes over time.
I have another question just out of curiosity. The first, the Californian data set you showed, right?
Yeah.
From I think the Nature Climate Change paper. So that was up to 2016. That sort of was foreseeing the sort of massive mortality events. What's happening now? We are 6 more years into the event.
It's I was not involved in that study, but it's a good question.
I'm curious. Yeah, did you know? Or you also don't know, because when I saw that, this ended in 2016. We have now 6 more years of data. For example, I'm just curious. Was that increase in autocorrelation? Is it continuing to persist? Has it come back to the background levels now?
These are great questions, but like these studies is like a lot of the work that we have been doing, that we always a posteriori look, and then like it's kind of look, it could have worked, and then you never go back into that to see, as you say, these details that you are highlighting now.
Okay, great. Lots of food for thought with data sets. Any more questions? Okay. Oh, you have a follow-up question. Yes.
Is it not possible to identify the time scale from the data set? So that the whole analysis will be will be in terms of some relative time.
To be honest, I don't understand your question. Can you explain it to me again?
Yeah, I'm saying that is there any possibility to identify the time scale of a particular process from the data set? So
his question is, can you identify the time scale from time series itself?
Well, I guess so. I mean, it depends on time scale of. I mean, for that case, you can see the seasonal dynamics, for instance, of the forest. So you would know that there's a seasonal time scale into that, which means that you would need to have more than just one season in your data set. But the question is, I guess, what is the time scale in order to, and based on that, to have enough data to analyze your signal, right?
Yeah, yeah. I mean, the autocorrelation time itself is a time scale.
True, true.
That also gives us some measure of time scale, right?
That's true.
Intrinsic
Yeah,
time scale in the system.
yeah, that's true.
I mean, you can plot the complete autocorrelation function, but 20 years data, how much can you do? Even
True.
at lag 10, you only have now very few data points.
These are great questions, but it's quite hard. I mean, I
With short
haven't
time
seen anyone.
series.
Yeah, I haven't seen anyone trying to infer, or maybe I'm missing that literature. Try to really infer timescales from the time series itself, or from these systems. Maybe for climate we'll do that.
I think, in many climate, you're right, I mean, in the climate science literature, when they have this, multi-time scale data sets, for example, these high resolution sensors, which go all the way from a few seconds to, years, they plot these spectral functions, and these spectral functions often capture these multiple time scales within the system really well.
Yeah.
And I know, I mean, I think Valerie here understand these methods much better than anyone else.
That's
Do you
true.
have any comments, Valerie?
As I said in my talk, much depends on data. There is lots of analysis that is data driven, and you can derive time scale of intrinsic phenomena in the data depending on the system. Thank you for the interesting talk, Vasilis. When I saw the title, I actually expected that you would offer the solution. I thought that you would go to forest authorities.
Hey, whether Vasilis, you can just unshare your screen, you can also see us.
Yeah. You're right.
If you unshare the screen now.
It's actually most challenging and most risky in this area of research is to say when exactly early warning signals will bring you actual transition. I think it is one of the most interesting areas of research in this area. And I actually try to do it, but of course it's not always working, because if transition even forecast correctly but reverses back, then you forecast fails. Nothing to do with that. But at least we can attempt to be useful, as they say, for stakeholders and policymakers, with some warnings, especially in those areas where such warnings can be low cost implemented. For instance, if you can replace some components, as I said in my presentation, if you can replace chip components early to prevent failures, or if you incentivize forest authority to pay attention to their dying forest, there is no harm in that, even if you so
Yeah, I can't hear you anymore. Oh, yeah, you're back, I think.
changed my microphone. I apologize. The sound was okay. I say that in many areas related to either very light costs or quick implementations, and in those that are useful for ecological reasons, I think we should be sending this message to policymakers. It's better to warn them with false positive than miss some critical transitions in these areas. That's my opinion. Thank you.
I agree. It's better to be precautionary than to be. I also share the opinion that we should try to be a little bit more conclusive than to say, something that yeah, the data is not there enough, or we can't really do that. I think that it's the time where we should be a little bit more affirmative, even if we're mistaken on the good side, like, oh yeah, do be careful. Okay, nothing happened, but it's better to be careful even if nothing happens than to say, okay, we don't know and something bad is going to happen. But
Remember,
sorry.
I remember several years ago there was a problem in Italy with the geophysicists who actually claimed they have operational forecast of earthquakes.
Yeah.
And they started warning when they thought it should be shaking. And then there was actual earthquake that they didn't forecast, and government wanted to take them to court. So I would not kind of start forecasting something that is highly uncertain and risky, especially if your forecast can be really inaccurate in many cases.
Yeah.
So we have to be responsible as scientists and clearly explain the areas where we can help and to what extent we can help, and communicate uncertainties as well. Although I have to say that policymakers often don't comprehend uncertainty correctly, because you tell them that uncertainty should be kind of plus minus. I remember this Stoltenberg, when he was Danish prime minister, there was, I think it was Copenhagen meeting. And one of the scientists told him that temperature should not rise more than 2 or 3 degrees. And he was started saying, tell us 2 or 3. We are policymakers, we have to know. And the scientists try to say it's uncertain, and he just doesn't understand what is uncertainty. So I think it's it should be communal effort to when we work in various areas and apply similar methodologies. We just have to explain stakeholders, and we have to be honest ourselves what we can and we cannot do, what is the limit of our research, especially in the area of forecasting. Thank you.
Absolutely, I completely agree with what you said.
Great comments, very important comments. We have seen the sort of, pitfalls of forecasting in the context of COVID, the ongoing pandemic, right? It's very, very, very difficult. Yeah, but we must.
But it doesn't mean we should not try to do it, right?
Yeah,
I mean,
we must engage.
Absolutely, it's actually exciting.
Yeah, exactly.
Look into future in some sense. Yeah.
Okay, great. So we have had a nice set of discussions. We take a tea break now and come back in half an hour, right?